Welcome back, everybody. Let's look at mass spec. Mass spec is a technique that takes a molecule, fragments it into smaller pieces, then it gives you a graph of the fragments. Then you take them and you put them together and try to identify the original structure of the molecule. It gives you a lot of structural details of the molecule. Let's see what happens inside a mass spec machine. Nowadays you have tabletop machines, and if you've gone to your lab you would have seen something that said GCMS, gas chromatography mass spec, or LCMS, HPLC, linked to a mass spec. So these are two very common pieces of desktop equipment you would see in your lab. Let's open the lid and see what's inside a mass spec. So we have to first inject a sample. There's a sample chamber. So let's say your molecule comes in and it's all bunched up here. And they're neutral molecules. We're not putting in ions here unless it's a chemical ionization technique. But here we're talking about an electron ionization mass spec, which are the most common and probably the most affordable. So the molecules are going to come in a bunch. So, and if you bombard them, you won't get much information from this pile. So we have to pull them out and pull them apart. So what we do is we reduce the pressure in the sample chamber. So the pressure here would be, let's say, 1/100th of a torr. And what happens inside? Well, the molecule then starts separating because very low pressure. The molecules start separating and then they start traveling through here. So after it passes through the sample chamber, it goes over, so they get separated, and then here is what you call a molecular leak. So it goes through here and it enters an ionization chamber. So the ionization chamber, just as the name implies, is where the molecules are going to get ionized. How does it do that? There is a very high energy electron filament here that's going to throw out a very high energy electron spray. Those are going to come down, and as the molecule goes through here, this is your filament and this is your anode, a receiving plate here. And as the molecule, so let's say we're trying to find the identity of a particular molecule here. So the molecule is then going to go through here. There may be different molecules, but if you are coming from a GC, you will see each of these molecules will be separated, and let's say this molecule enters the chamber. Right there, there's an electron spray that's about 70 electron volts here, 50 to 70 electron volts, which is very high energy. This is your cathode anode voltage difference. So that's going to hit that molecule at a very, very, very high speed and energy, and it's going to pull off an electron. And so you have an ion here. Now you have a molecule that lacks an electron. So that is sometimes called a radical ion or cations. These positively charged ions are going to go through here, and they are going to enter a chamber where you have accelerating plates. Now, even in here, the pressure is really very low, sometimes as low as 10 to the minus 8 torr. Some of the molecules will go right through without any electron impingement. Those molecules will be neutral and they will be sucked out by a vacuum. So you'll have the positive ions going through, and these, as you can see here, there are some negatively charged plates here. And there they will have an acceleration here, and so you would go at a very high speed through a focusing slit. You want to focus it so that it will go through this chamber. So this is your acceleration chamber. So this is your ionization chamber. This is your sample inlet or sample inlet chamber, and here's your acceleration. So these ions fly through these plates here, and they will go through this little slit, focusing slit, go through the magnet. So the magnet is quite powerful and it will accelerate it even more. Now, if all of the molecules come and fall at the same spot, then there really isn't any useful information we can get from just one big blob or peak. We want to be able to separate them according to their mass. And so this is why this is a curved chamber. And so it's like taking the bend, or think about, taking a turn. If you're really, really very light, you're going to get flung over and you'll have a big arc. Whereas if you are heavier, then you're going to have a smaller arc coming through, or smaller radii. And you're going to hit a quadrupole detector here. Now, not all of them are going to hit the detector. So what we do is we vary the magnetic field strength here from about 800 Gauss to about 5,000 Gauss here in the magnetic chamber. So you're going through different rooms or chambers. Magnetic field in here. When you go through this slit here and enter the chamber, the sample or the molecules will be separated according to their mass over charge. We are assuming they will all have at least a +1 charge, because neutrons and radicals are going to be taken away by the vacuum. So your positively charged molecules are going to be then hitting this detector according to the mass. So let's say you'll have a very low mass here, and then a very high mass here, and all of the fragments will be in between. Well, the lowest mass that you can have is a proton. The highest mass that you can have is the molecular weight of that entire molecule. In between, you'll have fragments, maybe this, and maybe this. So according to their mass, you will have different fragments. And so then that is going to then create, well, you have an electron amplifier in the detector, and that is going to send all that to a machine, and that's going to print out a mass spec graph just like this. So if you take the mass spec, any mass spec graph, the x-scale, x-axis, is mass over charge. Typically, the molecules are hit once and they have a +1 charge. If you have a +2 charge, that's very, very rare, and so you may have a tiny peak for that. So it's separated according to mass over charge. Now, in this graph, you can see there are lots of lines. So these are just talking about the different pieces or fragments that are arranged according to their mass. All of these have a charge of 1. So whatever the mass, that number that you see is the weight, AMU weight of that fragment. If the molecule came out and it has all of its parts, that would be the molecular ion peak. These are going to be fragments. And well, the lowest one you can have is a proton, which, it's very, very rare that you see that. But you can arrange them according to the mass over charge inside a mass spec just by the way it's designed. So this is a very nice way of finding out what the molecule is and what is the fragmentation pattern of this molecule. Putting that information together can give you the structure of the entire molecule. So let's look at what these peaks could mean. This is a octane here, molecular weight 114. And you can see at 114, you will have a peak. So the rightmost peak would be the molecular ion peak. Now for all of them, that would be the highest molecular weight. And I will talk about this later, but most of them would also have a very teeny peak next to it. Because if you remember, carbon has got two main isotopes, carbon-12, which is about 98.9%, and carbon-13, which is 1.1%. And carbon-13 is just 1 AMU higher than carbon-12. So all of them will have a teeny peak right next to them, which is their M+1 peak. But the most important information for us is this peak here that is rightmost, and that is noticeable. That's the molecular ion peak. We can get the molecular weight of that molecule from there. So if you don't know the molecular weight of your unknown, shoot it in a mass spec. Take the rightmost peak, that's your molecular weight. Then these are the fragments, and you will see a peak that would be 100%. So the Y scale is the relative intensity or relative abundance. What does that tell you? So coming out of the mass spec, you would get more hits for this fragment than for any other fragment. Let's say you got 100 hits for this, or 100 fragments of this coming through. This one, on the other hand, which is at 20, would have only 20 fragments coming out. And this one, the molecular ion, would have just 5 fragments coming out. So this is basically counting the number of fragments coming out, and that's your relative intensity. Now that is it's a percentage. So this is basically what a mass spec would look like, and this is what the machine would look like. Now, I would like to also say that, well, you have a detector here and an amplifier. So let me mark those out. Detector and amplifier. Sending it to a computer that is just going to generate your graph. So in summary, I'd like to say that when you shoot a sample inside a mass spec machine, it is going to vaporize into neutral molecules, and it's going to then travel through a little molecular leak, and it's going to come into an ionization chamber where you're hit with very high energy electrons. These are going to knock off some electrons from the molecule, and so that is going to become a positively charged molecule. So now your particles are going through, and they're going to be positively charged. The molecule here, when it's hit by an electron and ionized to a positive charge, it is going to unravel and break into several fragments. All these fragments are then going to get accelerated through the machine, and it's going to go focus into a magnetic chamber where you are going to vary the magnetic field to make sure all of those fragments hit a analyzer, mass analyzer. So that's a quadruple mass analyzer here. When it comes to the magnetic chamber, it's going to be separated according to its mass and charge. If the charge is 1, then your mass is going to be what you would see here for the main peaks here. So it's going to hit the analyzer, and you are going to then see different peaks for different masses. And that information will go through an electron amplifier, and it's processed in a computer to give you a mass spec. And the important thing is this, the first peak on the rightmost or the highest molecular weight peak would typically be the molecular ion peak. I'm saying typically because in some cases the molecular ion fragments to the extent that you can't even see it. But for the most part, you'll be able to see a molecular ion peak. Then the tallest peak would be the one that is found most abundantly. So this Y scale indicates how much or how long they can spend or how stable they are inside the mass spec to go all the way and hit the detector. So if it is the highest abundance here, because you have more of these fragments than, let's say, these. The more stable they are, longer the shelf life, the more you're going to see them hit that detector. So let's look at how they fragment inside. Let's look at what these other peaks mean. Let's look at, in general, fragmentation patterns. I will then talk about different functional groups in other videos. Let's look at a generalized view of what each of these functional groups would typically do inside a mass spec when it's hit by electrons. Let's write down what we just talked about here. One, molecular ion peak has the highest m over z value. 2, the base peak is the most stable or the most abundant, mostly because of its stability, and is set to 100% intensity. It says relative intensity because all the others are measured against the base peak. Most of our information comes from the m over z here. We look at the base peak here and the fragments that are kind of about 15 or 20. We don't look at all the tiny little sister peaks here because that would be too numerous for us to analyze. Now, what happens inside? When you have an electron attack a molecule, it knocks off its teeth. So electrons are lost in ionization chamber and form radical cations. And let's take a look at what it can be. Radical cations. So the electron that's most easily dislodged is a lone pair electron. So lone pair electrons, let's say you have an alcohol here. Alcohol's got lone pairs and bond pairs. It's easier to knock this off. So the electron comes in and takes off one of the electrons inside the ionization chamber, which is then going to leave you with a radical cation. So here, why do we call it a radical cation? Because there is a radical here and there's an empty spot there. And if you look at the formal charge of this, oxygen's group 6, but it has 1, 2, 3, 4, 5 in here. So therefore, it will be positive. This is called a radical cation. The radical cation is then going to unravel inside the machine when it flies through. And how does it do that? It's going to pull electrons away from other parts of the molecule because oxygen's electron negative. It wants to have those electrons. So let's take an example. Let's say this is just a very favorite molecule, which is ethanol. And ethanol then has a hole. I'm going to put the hole on this side. The hole is a positive. It's just an absence of electrons. Now, two things can happen. You can either pull off both electrons here. That's inductive cleavage or heterolytic cleavage. And so you can have two pathways for this typically inside a machine, not just for this, but for most molecules. So you can have a pathway where you have heterolytic cleavage, or you can have a pathway where you can have homolytic cleavage. Let's look at our inductive cleavage or heterolytic cleavage. Heterolytic or inductive cleavage, meaning you're breaking it up. I'm going to redraw this again. So here you're going to have the same molecule come over. And over here you have a positive here that is going to pull these electrons toward itself. Literally break that sigma bond. And now you're going to have a fragment on this side that is bereft of electrons here. That's lacking a pair of electrons to make the octet. So you have 1, 2, 3, 4 minus 3 is a positive charge. This is then going to become an oxygen that has got 2 electrons from here, from the bond. 1 electron was already here, and so now your positive charge goes away. And if you take the formal charge of this, you have 1, 2, 3, 4, 5, 6, which is a 0. So this is a hydroxyl radical. they are not going to be accelerated by these negatively charged plates. They're just going to go through the vacuum. This is what's going to come down and hit the mass analyzer and give you a peak m over z here at 29. You see these 29 peaks a lot. Most molecules will have an ethyl fragment. Now let's look at what happens when you have a homolytic cleavage. So this is another pathway. And what happens here is you would have the same molecule here. I'm going to redraw this. So it's coming over here, and you have a ionization that has already occurred here. This is going to pull electrons from the neighboring bond. You can also call this alpha cleavage. So here, this is going to hold hands with this electron and make a bond. It's like a radical reaction that you've seen before. This is going to go with the rest of the molecule. And this could be a very long chain or a short chain. It doesn't really matter. We're just breaking that right next to the OH. This then becomes a double bonded fragment. So here's your CH2. We took that bond here and put it over here. Now, if you do the formal charge here, this electron went over. So you have 1, 2, 3, 4, and 5, which means you have a positive charge here. So this is then going to go in and hit the detector. And the methyl radical is then just going to go through the chute, and you'll never see it again. Gone. Don't worry about it. This is the guy that we need to think about. And you will get a m over z peak for this at 31. This is just a lone pair. So this is a pathway for removal or loss of lone pair electron. And we can have a lot of these. I mean, we can do this in other elements, not just oxygen. For example, let's say you had a chlorine here. You would see a very similar pathway for that too, a chlorine or a bromine. Let's say you have a molecule like that. And you have the same attack on that takes off that electron and leaves a hole in here, and that becomes your radical cation. Now, sometimes the books might just put it like this. So they might just put it out like this, or they might draw it out like this. It's the exact same thing. We're just showing you where exactly it is. This is better for drawing mechanisms. So let's look at what are the possibilities for this radical cation right here. What can we do with it? Let's look at two possibilities, just like here, heterolytic and homolytic. Let's look at this one. Let's say we're going to do a homolytic here, which means you're going to have radicals holding hands and making bonds. So here's a chlorine radical here, and it'll pull these electrons. Chlorine's electron negative. It's going to unravel by pulling those electrons to itself and making bonds here. And so the sigma bond is going to split into there, and you are going to get a radical, ethyl radical, plus a double bonded chlorine. And here you have only 1, 2, 3, 4 electrons remaining here, because this electron is going to make a bond. And here's your CH2 that I'm going to just hydrogens here. And if you look at the former charge, 1, 2, 3, 4, 5, 6, you need 7 if you're chlorine, because that's who you are on the periodic table. You would get 7 minus 6, a positive charge. And here's your ethyl radical, which you're not going to record here. You're only going to record this mass on the mass spec. Let's look at the other possibility. Let's look at the heterolytic cleavage here for this molecule. So if you want to do a heterolytic, you are going to take the same molecule here. Let's do the same one here, the radical cation. In this case, because the chlorine's electron withdrawing, it's just going to pull both these electrons to itself and run away with it. So you are going to then have a propyl cation, because you pull both electrons out of here. You have an empty hole. So you only have for formal charge 4 minus 3 a positive. And you are not going to see this on the spectra because if you look at this, you will have a 0 formal charge. And that's going to go through the chute. So that is going to be m over z 43. So we can see that you would get different fragmentation patterns for the same molecule depending on the pathway. So you can get a, let's say, a 49 or a 43, and you would then piece it back together and try to guess what the original structure is. Now, you may also get more fragments by this fragmenting more and giving you a 28 and a 15. So it's going to break up even more. So it's going to keep going, and you will see that, well, if let's say you do this over here, you will get a fragment from here that is a CH3 plus, that is a 15. Or if you did, homolytic, you might get a fragment that is 28. So you have a lot of possibilities for fragmentation, and that's what we're going to talk about for the rest of this chapter or for this topic. Mass spectrometry, fragmentation patterns. We're going to take different functional groups and see what happens. We talked about what happens to a single bonded molecule in a machine. What if you have multiple bonds? Let's say you have pi bonds. What happens then? Well, nothing really drastically different from here. We can see very similar patterns. Let's look at, let's say, a carbonyl. You see carbonyls all the time in machines. Carbonyls are in compounds. Carbonyls are in ketones, aldehydes, carboxylic acids, esters, anhydrides, acid chlorides, and the list goes on. So what happens when you hit one of these? Let's say you shoot a bunch of molecules, the GC separating according to their dipole, and they're coming into the mass spec one at a time, getting hit by these electrons, high energy electrons. Well, you're going to get your teeth knocked out pretty much. Let's look at the hole that we created here. We chipped off a tooth. So let's look at the hole that we created here. We have a empty spot here, which means the formal charge of this is going to be 1, 2, 3, 4, 5. 6 minus 5 is a positive. So for all of these fragments, it's really important that you do a formal charge calculation. So formal charge, oxygen is group 6. So group number minus sticks plus dots. We did this earlier. And here you have 1, 2, 3, 4, 5 dots here. Therefore, this is going to be 1. So we have a plus 1. We can take this and fragment this molecule even more. Now oxygen's a plus. It's really unhappy. It's electronegative. On top of that, it's got a positive. It's going to pull out the electronic can from its neighbors. So here are two alpha carbons here, and they are going to get their arms severed. So here your lone pair is going to come in and make a bond right there. So you will have a carbon, and now you are going to have a triple bond. You have this oxygen here, one of the remaining electrons taken up, so you only have one lone pair. If you do the formal charge for this, same story, 1, 2, 3, 4, 5, 6 minus 5 is a positive. It's a whole positive charge there on that molecule. So this is going to have a m over z of 43. And it's going to strike the mass analyzer, and you're going to get a peak for it. And, well, this part of the molecule, well, if you take that, that's going to be neutral. It's a radical, it goes sucked out of the machine. So this is a typical fragmentation pattern for carbonyls. You can also do a fragmentation on this side exactly the same way. So instead of pulling this electron, you pull this off, and you'll get a 15 going out the door. Well, do we have any more? Well, if you have a longer tail, let's say you have a tail that's got, more carbons, we can do alpha, beta, gamma cleavage. Let's look at that. So here's a carbonyl. And 1, 2, let's see, we have a little longer chain there. tail, and the tail's wagging, and it's going to get chopped in the machine. Let's see how. Let's do the same thing. We're going to hit it in the electron ionization chamber, knock off a tooth there, create a hole, and now it's going to grab anybody and everybody to fill in that hole. So here is, that's gone, and you have a positive here. Well, we know that it's going to grab the alpha, but let's try to do something different because we are going to see peaks for this. Let's say alpha, beta, gamma. So it's going to wind around, and you can have other groups over here. Let's say, well, yeah, methyl, ethyl, propyl, whatever you want. In this case, the gamma hydrogen, if you look at it, 1, 2, 3, 4, 5, 6, and you know 6 is a very nice ring, and so that's what's going to happen. You're going to grab that hydrogen here and make a OH bond, but that would be too many for that hydroxygen, so then it's going to fragment it like this. These electrons are going to make a bond there. This has to go somewhere. Well, there's another electron here on that sigma bond. You know, 2 electrons per sigma bond. They are going to go hold hands and get out of the machine, neutral. Let's look at this fragment, see what it is. So here is your carbon. Now you broke that pi bond, so you only have 1 bond here. You have a hydrogen over there, and you made a double bond. Now, over here you have 2 electrons, and that radical's there. If you do the formal charge for this, 1, 2, 3, 4, 5, 6 minus 5 is a plus. So this is a radical cation. The radical cation is going to go hit the detector, and you're going to get a P for that. And you're going to have the ethyl, or this propyl, or whatever. Let's say you have an R group here. It's going to run out of that machine with that double bond here. It's going to be neutral. So it's not going to hit the detector, and you are not going to get a peak there. There's another hydrogen here. So that's called gamma cleavage or McLafferty rearrangement. Now you would think these molecules are going at like microsecond, even higher speeds through this machine. Where is the time to rearrange? Rearrangements are fast. That's what we found out. And rearrangements are obeying all of the rules of regular reactions. It is subject to the law of mass action and charge. So if you take the mass and the charge here, it will be equal to, let's say over here, it will be equal to the mass plus charge here. You don't lose anything once you hit that radical cation. You would see your law of mass action, and charge is going to hold. Well, do we have any more? Let's do a couple more fragmentation patterns. If this is all too much for you, just turn it off, come back and watch it another day. But since I have space here, and you know how much I love to fill in the spaces, I'm going to do one more fragmentation pattern. Let's say we have rings. I've been doing long chains. Let's say I have a ring. Well, what then? Do we not have all of this? We'll have different things to do. Let's say I have a pi bond. We also have only done carbonyls. What about pi bonds? Don't they get attacked? Of course. So if you have a choice, when you put this through the machine and you have a choice of pulling out the pi bond versus pulling out the sigma bond, pi bonds are a lot weaker, and so those electrons are the ones that are going to get hit. And so you have your electron ionization here happening right here, and that's going to take out that electron. So you would have a carbocation, and we talked about the stability of carbocations, and tertiary is the most stable. So chances are that's where you're going to get your positive, and this is where you are going to get your radical. Even though it's tertiary and it's stable, you still are going to get fragmented into smaller pieces inside the mass spec. What can this do? Well, this can then unravel the entire molecule. It can pull electrons here, make a double bond. This can pull electrons here, make a double bond, and this can go over here. So basically this positive charge is like pulling electrons here and breaking this up. So you would have this come off as a alkene, and that would be neutral if you have, well, we have two hydrogens here. I'll just draw them in for reference. So here is your alkene that comes out 28, and the rest of the molecule is going to be like a butadiene radical cation. So you have a double bond here, and we had our double bond right here, same here. Over here you have a radical cation. We can draw this as a radical cation like that and put a positive like that. So this is something that can happen in cyclic compounds in a molecule, especially six-membered rings. And you know, when these two come together, that's called a Diels order. This is the reverse of that. So this is called retro Diels order. So there are lots of other patterns, but these are the ones that you're going to be encountering a lot throughout the other functional groups. So this is just a presentation of what are the possibilities when that molecule gets hit by an electron and travels through that tube at breakneck speed, literally breaking its neck. Just in summary, we want to talk about some of the fragmentation patterns inside a machine. So once the machine neutral molecule goes through and gets one of its electrons knocked out, then the molecule begins to unravel. Most of the time, the molecule would get its lone pair electrons knocked off first. And so it would have a radical cation. The radical cation can pull both electrons out in a heterolytic cleavage or inductive cleavage and give you a cation for the remaining fragment. Or it could cleave the bond next door and make a double bond, pi bond there that is positive, and have a radical go out. And you see this over and over again with other heteroatoms. Now there are other pathways. If you have carbonyls, you can do the same thing and get a alpha cleavage over here where your electrons are going in different directions and giving you one of these triple bonded carbonyl bonds. You can also get a gamma cleavage by pulling off a hydrogen at the gamma position relative to this carbonyl and giving you an enol that is a radical cation. These are all very short-lived, and when they go through the machine at super high speeds, they hit the detector and you will get a peak exactly where that mass is. For each of the masses, you would get a peak if it is a radical cation or a cation. It's the same thing if you have cyclic compounds or pi bonds. You can have a positive charge that's formed by knocking off an electron, and this is a radical cation here, and that can then unravel the molecule by doing a retro Diels order here. So these are some of the patterns. We will see a few more, but when you come back and see the other functional groups, you would recognize these patterns over and over again. So just to leave you with some thoughts, mass spec is a fantastic method of finding the molecular weight of an unknown and also come up with an identity by analyzing the fragments that come out of the mass spec. In modern mass specs, the computer already has a library of mass spec fragments that are possible for each molecule, and it can even give you suggestions and identify the molecule for you. So this is a very powerful technique. It's used at airports, it's used for finding out pollution, it's used for proteins, DNA, basically for all of the pharmaceutical compounds out there. Anytime you have a new compound that's invented, you have to put it through a mass spec to identify the molecule. All right, guys, so this is a powerful technique, and we will see you with a lot more molecules in the near future. Talk to you soon. Bye.